Hello, and thank you for attending this installment of Thorlabs webinar series. My name is Chris Hensley, and I, along with Ethan Baker, are part of the team that developed Thorlabs' line of Q-switch microchip lasers. Since the release of these high pulse energy lasers, customers have been coming to us at Thorlabs asking about novel applications. The intent of this talk is to describe our laser and some of these interesting projects. At this point, I would like to introduce our speaker for the day. Ethan received his Bachelor's of Science in Electrical Engineering and Mathematics from Michigan Tech University, where he concentrated on photonics. Originally joining as an applications engineer in our technical support group back in 2021, Ethan now works with our short pulse laser development team, developing lasers and amplifiers capable of producing picosecond and nanosecond pulses. The lasers Ethan will describe today are some of the highest energy lasers in our catalog, and as we shall see, are capable of some novel laser processing. Throughout Ethan's talk, please feel free to submit any questions you have using the Q&A tool. He will be answering any questions at the end. With that, I will hand it over to Ethan to discuss how these lasers operate and some of these customer-inspired applications from our line of Q-switch lasers.
Thanks, Chris. Hi, my name is Ethan, and I'm here to talk to you today about harnessing the power of Q-switched lasers, from laser-induced breakdown spectroscopy to micromachining and beyond. So let's get started with a brief overview. We're going to begin by talking about what a Q-switched laser is, some common specifications you'll see when you're looking at data sheets, and then we'll go on to talk about how they operate. Then we'll move on specifically to talk about our Q-switch laser, one of our Q-switch lasers, the QSL-103A. We'll talk about some features it has that makes it notable. We'll take a look inside to see how it's designed, and then we'll look at some applications. In particular, one application we're going to focus on is called laser-induced breakdown spectroscopy, or LIBS. We'll begin by talking about some applications of LIBS. We'll show you how we implement it here in our lab, and then we'll move on to showing some results we got with our system. So to start, let's talk about Q-switched lasers and what kind of specs you'll typically see when looking at a data sheet. Now, when we think Q-switch lasers, we're typically thinking high pulse energy. These are some of the highest pulse energy lasers we have in our catalog, as Chris mentioned. Typically, you're thinking somewhere in the microjoule to millijoule range. Now, wavelength is a little more complicated. Typically, these are near infrared, but there are a few notable examples in the visible and UV. In particular, praseodymium YELF lasers will laze at 640 nanometers. There's also second harmonic generation and third harmonic generation, which can be used to get you wavelengths in the green or in the UV. Now, in terms of pulse width, this depends in large part on your pulse energy, but you can see anything from tens of picoseconds to tens of nanoseconds. Repetition rate as well depends largely on pulse energy, but this could be anywhere from a tenth of a hertz to tens of kilohertz. And peak power is another application where these lasers shine, and that we're typically looking at somewhere in the kilowatt to megawatt range. So how do they work? Well, we're going to start by looking at a CW laser, a continuous wave laser, and then we'll show you how it differs from a Q-switch laser. So here with a CW laser, we've got a constant pump power. It's constant light coming into the laser. We drew our pump diode on the top here. That's not quite accurate, but you'll see we have a pump diode, an input mirror, a laser crystal that may or may not be doing some wavelength conversion, but that's what's generating our laser output. And then we've got an output mirror. Now, for a CW laser, this output mirror is typically only 99% reflective, for example, and that 1% of light constantly being leaked out is where we get our constant output power. Now, that's all well and good, but what if I'm not getting enough power for my application? What if I've got some high peak power application and the CW laser just won't do? Well, that's where you need a Q-switched laser. And what I want you to think about when we talk about the method of operation of a Q-switched laser is these buckets at the water park. For those of you who aren't familiar, you'll see these at a water park. They're large buckets, usually on top of some sort of roof or awning, and they're constantly being pumped in with water, constantly being filled, and they get full and full. And once they're so heavy, so full of water, they will tip over due to the weight of the water. And all the water comes pouring out on all the people. So at a water park, this typically would have a rep rate of maybe 4 times an hour, maybe every 15 minutes, this bucket gets filled and dumps out onto all the people. And this is exactly what we're going to do with our laser cavity. So looking here, it's very similar to the CW laser we were just looking at. We've got a constant pump power, we've got a pump diode, input mirror, laser crystal, and output mirror. But what's different here is our output mirror. Instead of allowing that 1% of light to constantly leak out, what we're going to do is we're going to confine that light to the laser crystal and let the power keep building and building until eventually we let the pulse out. And this pulse that comes out has a much higher peak power than we would have got through a continuous wave operation. So that's how it works in theory. We're going to look at a bit more realistic depiction in this next slide here. So here we've got our pump diode on the left coming in through the long axis of the laser. We've got an input mirror, again, our laser crystal, which is performing our lasing. And what's different here in the CW case, as I said before, is the output mirror. Now, there's two things that make this different. One, we've got a dichroic mirror here that may be in a CW laser. The function of the dichroic mirror is to separate the pump diode wavelength from the lasing wavelength. What really allows for that Q-switched operation is the saturable absorber. The saturable absorber is what's acting like our bucket at the water park. When the energy inside the laser crystal is low, that saturable absorber acts like a mirror and allows energy to keep building. When the energy inside the laser crystal is high, that saturable absorber acts like a window and allows our pulse out. So when you're talking about Q-switched lasers, you'll commonly see some graphs like this. The energy stored in the laser cavity is linearly increasing as long as the pump is on, and then all the power comes out at once when we open up that window. So we get that sawtooth wave up top, and then our output power, you only get a narrow spike when the energy is released. And that's what allows for such short pulse widths out of a Q-switched laser. So now that we understand how they work, let's talk about some applications. Micromachining is a large application, so I want to take a little bit of time to show a typical micromachining setup. Here we've got our laser. We've got some conditioning optics. In this case, it's a collimator to collimate the beam and a beam expander. That beam expander will allow us to get a smaller spot size on the other end. Now here we've got a galvo, which is scanning the beam across the surface of our sample, and that allows us to choose whether we're making a circular hole or a square hole, allows us to engrave all sorts of patterns. That's where your steering comes from. We've got a focusing lens, and then we focus our light onto the sample, and that creates a plasma which ablates or removes material from the sample. So that's a generic micromachining setup. And here's some applications of what you can do with it. On the left here, you'll see we're machining a razor blade with our laser here. It's just a typical stainless steel razor blade. And on the right, you see an example of the kind of holes we're able to produce. So that's a 50 micron square hole. 50 microns is about the average diameter of a human hair. Another common application you'll see is medicine. When you think of laser surgery or cosmetology lasers, these are most commonly Q-switched lasers. For things such as tattoo removal, but also treating lesions or other various things on the skin. And the reason they're mostly topical in medicine is because these near IR wavelengths don't penetrate the skin that well. You can also use them inside the body to create bloodless cuts on organs or other tissue, but you first have to open the cavity up because the penetration is just not that great. Lastly, nonlinear optics is an application that's interesting to a lot of people. In this example, we're showing second harmonic generation where we've got the same setup before. This whole bit on the left is the same Q-switched laser we were looking at, but now we're taking the output power, we're focusing it through a lens, and then this nonlinear crystal performs second harmonic generation, in this case to produce green light from near infrared light. So now that we've talked about some applications of Q-switched lasers, let's talk about one of our Q-switched lasers. This is the QSL-103A. It's a 1030 nanometer picosecond Q-switched laser. And one thing that's really unique about it is the beam quality on this is excellent. Guaranteed to have an M squared less than 1.2, but typically we're seeing values around 1.1 or even less than 1.05. Additionally, it's got a sub-nanosecond pulse width, typically around 500 picoseconds, and that will enable some unique applications we'll see later. Additionally, it's quite compact. It's got the footprint about the size of an iPhone for just the laser head, and you'll see the controller unit's not that big either. So taking the lid off and looking at the design, you'll see this is the same setup we were looking at before, just smaller, more compact. We've got our pump diode. We focus that through an input mirror into our laser crystal. And that produces our laser light, which then goes through our output mirror, which has our saturable absorber on it. One thing you'll notice here is the laser crystal is quite short. And we actually bond these crystals ourselves here at Thorlabs, which is quite nice and allows for some customization. Now that we've seen what the GSL or the QSL looks like on the inside, let's talk about some applications that customers have asked us to perform with it. Color marking titanium. This is a typical micro machining setup you've seen before, but this time, instead of trying to drill a hole or etch a pattern, we're simply trying to change the color. This is analogous to the bluing of steel, although titanium is unique in that it allows for a few more colors. By varying how long the beam stays on the surface, we're able to change the oxide layer, the thickness of the oxide layer that's left on the titanium. And then through thin film interference, that produces the colors you see here. Another interesting application is diamond marking. Q-switch lasers can be used to mark diamonds in the same way you can mark steel. Why you would want to do that is mostly to put information about the stone, such as its geographic origin and its current owner. And second harmonic generation, I mentioned earlier, people do it with all sorts of Q-switched lasers, and we do it with ours here too. Same setup we were looking at earlier. We've got a pump diode, focus into the laser crystal. We take that output light and focus it into a nonlinear crystal. And the reason you'd want to use a Q-switched laser for these nonlinear applications is because these nonlinear effects get stronger with increasing pump power, or increasing laser power, that is. And so you're able to get more second harmonic generation conversion efficiency using a Q-switch laser than you would with a CW laser. It is possible with the CW laser, it's just not nearly as efficient because these are nonlinear processes. Nitinol stents. This is another medical application. So a stent is a medical device that holds a tube open in the body. It could hold open a biliary stent. In this case, that keeps open the tube that goes from your gallbladder to your liver. Or you'll also see them in the heart as well to hold open arteries. What's unique about nitinol is that it's a shape memory alloy. So nitinol has a special property where you can form it into one shape at one temperature, then change its temperature and its shape. And when it reverts to the original shape, or original temperature rather, it will have its original shape. So what they do here is they cut stents out of nitinol by making these holes, this lattice of holes, leaves that stent behind. Then once the stent is formed at body temperature, it's crushed and cooled down so that it can be more easily implanted inside the body. And then as the human's body temperature warms that stent up, it takes the form of a stent. That's a very unique application. We are able to process nitinol, as you see here. These are about 150 micron holes. Non-thermal machining. Now, this is why the pulse width matters. We were talking about this earlier. So at 500 picoseconds, we're right on the threshold of thermal machining. If we dwell too long on the surface, we will heat the material. But if we move fast enough, we're able to ablate without significant heating. So what you see here is a match head. You know, if this gets too hot, it's just going to burst into flames. Yet we're still able to machine it with a laser. I think that's neat. Now moving on to a very special application. I mentioned it before, laser-induced breakdown spectroscopy, or LIBS. So what is it and how does it work? Well, in a nutshell, we're going to take the same micro machining setup we had earlier. We're going to take this laser, we're going to do some beam conditioning, we're going to steer the beam around and focus it onto a sample. As we talked about earlier, that creates a plasma. Now, instead of caring about the removal of material, what we're going to do in LIBS is capture that plasma light and analyze the wavelengths coming off the plasma. And by doing that, we can determine the elements that made up the sample we were just ablating. That's a very interesting application, almost forensic it feels sometimes. You can take an unknown material, zap it with a laser, and simply by looking at the plasma that comes off of it, determine what it was that you just zapped. So how do we do that in our lab? Well, this looks, as you can tell, a lot like the diagram we were just looking at. We've got our laser, our conditioning optics, our scanner, got a lens. In this case, we're using a fiber to carry our light from the plasma source here at the sample all the way behind this plate here, back through here. You can't really see the fiber, and then it goes into our spectrometer. So some unique things about this setup, it's got a quite broad wavelength range, 200 nanometers to 1,000 nanometers. A free-running acquisition. We don't gate our detector at all. And this allows for something unique called time-resolved LIBS, where we can leave the system running with the material on it. And as we drill through different layers, we can see how the chemical composition changes. This is also very useful for scanning objects that aren't one uniform material, such as rocks, actually, which is why one customer came to us asking if we could create this system. But we had a customer in the geologic space who was interested in using this on rocks and other mineral samples, and they asked if we could create a system that was capable of LIBS. And we thought about it. We looked at their requirements. They wanted something compact. They wanted this broad wavelength range. And what we realized was we have basically every part in the catalog that we needed. We didn't have to go to outside vendors to get the parts for this LIBS setup. Just by looking at the Thorlabs catalog, figuring out what we needed, what kind of specs we were looking for, we were able to get everything we needed just off Thorlabs.com. So that was really neat. So this is our system here. You can see it looks just like that diagram, as I mentioned earlier. But the scanning heterogeneous objects and the time-resolved application is something that's really unique to the short pulse width of the laser. Because we're not heating the material that much, we don't get as much black body radiation. In a larger LIBS setup, you'd be using a bigger laser, much more heat produced, and you have to wait for that black body radiation to disappear before you can take your measurements. So time-resolved LIBS isn't possible with a larger laser or a more typical LIBS system. That's one unique part about our implementation. So now that we've talked a bit about how laser-induced breakdown spectroscopy works, where is it used? Well, the most famous example of LIBS is on Mars right now. Inside the head of the Mars rover is a unit called ChemCam, which stands for chemical camera. And one thing unique about ChemCam is that it's only got one laser, but it actually has 3 different spectrometers. And the reason for that is they're looking for very specific things on Mars. They're looking for rocks that contain water. So they don't need information about the entire spectrum. They only need enough information to identify these different kinds of rocks and identify whether or not they contain water. So they use more narrow wavelength ranges, and they get a higher accuracy on their spectrometers that they're using, albeit in a narrower range. Another example is scrap yards. So in a scrap yard, you get all different sorts of metal sent to you, and different kinds of metal have different values. So if you can tell exactly what alloy you're holding, you can get the most bang for your buck out of that. As a result, they make these handheld systems here. That's a LIBS analyzer. There's a Q-switch laser in there and all the other parts we were just looking at. Q-switch laser, a focusing beam, some way to get the light back in and measure it with a spectrometer. And the user, quite simply, presses that object, it's about the size of a cordless drill, up against the part. They press a button, and now they can see exactly what kind of alloy they have. So those are some big examples. Now let's look at some examples we performed in our lab. As I mentioned earlier, we were looking at rocks and geological samples in great deal. So we started with limestone here. Now limestone, in theory, is composed purely of calcium carbonate. So the only lines we should see here are calcium, carbon, and oxygen. Obviously, that's not what we see here. The biggest contaminants we were able to notice were aluminum and sodium. Now, obviously, aluminum and sodium are constituents of limestone, but these are actually associated with a mineral called albite that's commonly found on the surface of limestone. So by looking at these results, we can not only determine that, yes, there is some calcium present, but we can also determine that the part of the rock we were hitting was not a part that was pure limestone. We can tell that we were hitting this scaled surface, kind of hitting that scale on top of the limestone, and that's where we get these stray elements from. Another example, we're looking at granite, and this is a much purer signal. You can see there's 3 main lines we detected: aluminum, sodium, and oxygen. Now those aluminum and sodium, we were just seeing them in the last one. Well, this is actually a related mineral that's found in granite. So by looking at these results, we know not only that we were hitting a piece of granite, but we know that we're hitting that pink feldspar specifically, because we wouldn't get the same data from the black biotite or the white quartz. And lastly, we also took a look at salt. Now, salt is sodium chloride. It should only have 2 elements, sodium and chlorine, and that's exactly what we see here. That's very promising to see. You'll notice that sodium peak is right there around 580. That's an orange color. And when you're ablating the salt, the whole crystal does glow this lovely orange. Very pretty. For our last example, we're going to talk about Canadian nickels. These are very unique. They've got 4 layers to them. There's a core of steel. It's most of the coin. Then you've got a thin layer of nickel, a thin layer of copper, and another thin layer of nickel. And so because our system is time resolved, because it doesn't produce as much thermal energy as a larger system, we're able to see the transition between these layers as we drill through it. And that's what I would like to show you guys next. So I'll set up the video here. All right, so you can see our system here, the coin's in the top right corner, and we're scanning across the surface, so the values will change a bit. Copper is defined by these 3 peaks in the middle here, that right there, very strong. Nickel is defined largely by these peaks down in the UV over at 200 nanometers or so. So you'll see as we go on the edge between copper and nickel, we see bits of both back and forth. Now, iron is right there. These peaks around 300 to 400, these are unique to iron, and that's what we're seeing as we start to get through the steel core. Now, you may notice that there was still some nickel in there too at the end, even though we were in the steel, and that's of course because nickel is a component of steel. So moving on now, I'd like to talk about some key components that made this possible. Of course, it couldn't be done without the QSL-103A. That's the laser system we used throughout this. Our Galvo was an XG series made by Thorlabs. And our Galvo was a slight custom in that it took an analog control signal directly. And most of the Galvos you'll find on our website are digitally controlled. The XG part of that determines mostly the size and the size of the beam it's able to take, as well as the scan angle. And the Y1HP part describes the specific high-powered laser mirrors we were using on this unit. Now, the fiber I didn't talk about much, but its choice is quite important. We chose a fiber bundle with 7 fibers inside. And more specifically, it's a round to linear fiber bundle. So at one end, all the fibers are bunched up in a round. The other end, they're all linear. And that's important because we want the round end to collect the most plasma light we can. But when it goes into the spectrometer, we prefer a linear end to better align with the slit inside the spectrometer. And lastly, speaking of spectrometers, we use the CCS-200 for this application. We needed a very compact spectrometer. That was one of the requirements from our customer. And of our compact CCD spectrometers, the CCS-200 has the widest wavelength range. So that's what we chose. All right, now I have some brief image credits to get through. And then I'd like to thank you all for attending. This has been a wonderful talk. I'm very glad I was able to present this to you. Now, moving on to Chris, I believe he has some Q&A questions for us.
Thanks, Ethan, for your presentation. We already have a few questions. Again, I'd like to invite you to submit your questions at this time. The first question we have regarding the spot size of the beam you're seeing. So do you have an estimate of what the size of the beam you're achieving is?
Yes, so we are using a 60 millimeter focal length lens right now to focus the beam. And so combining that information with our 8 millimeter input beam before the focus, we expect we're getting around a 20 micron spot. We can change out to a longer focal length lens. That will give us a larger spot, so slightly less ablative efficiency, but it gives you a wider depth of focus, which allows you to machine rough surfaces better. So there's a bit of a trade-off in focal length for those lenses.
Yeah, that speaks to some of the configurability of our system. So as Ethan showed, this was all developed in Thorlabs components. We've had customers asking, can they add an alignment laser, or can they polarize the beam going in, changing the focal length of the lens. These are all things that are easily customizable using Thorlabs components and the cage mounted configuration. We have another question asking about the speed of the scanning as well. I actually just checked with our team over in New Hampshire that builds these. She says for small angles that we're doing, maybe like 1 millimeter spot sizes or scan areas, you can scan up to hundreds of hertz. So very fast scanning with these Galvo devices.
That's right. And one thing I didn't mention earlier, the reason why you want to scan at all for a LIBS application, if you're not moving the laser across the surface of the sample, you will very quickly ablate all of the material in the focus. After 1 or 2 seconds, the laser isn't hitting the sample anymore because it's destroyed everything in the focus of the beam. And so your signal goes to nothing quite fast. And so that's why you need to constantly be scanning, or else you'll simply drill through the material and now you're not getting plasma anymore.
And then we had a question about collection. I think you may have touched on it at the end, but maybe talk about the linear to circular bundle of that fiber.
Yeah, so the plasma distribution of light coming off the surface is not uniform. So there are some angles at which you'll get more light and things like that. So for that reason, we want a round bundle to approximate a giant circular fiber as much as we can. However, if we had simply used, say, a 600 micron core multimode fiber, then we would have issues coupling into the spectrometer. So to get maximum efficiency coupling from the fiber to the spectrometer, you need a linear bundle. But because the distribution of plasma is not even across all of 3D space, a linear bundle will actually hurt your collection of the light at the plasma. And so that's why we use a round to linear bundle. It's also worth mentioning, these are specifically low OH fibers, which transmit the UV better. So the fiber can also be your spectral bottleneck if you're not careful. If your fiber is a narrower wavelength range in the spectrometer, then you're going to be losing information.
Sure. You showed a lot of metal and mineral samples. Have you been able to investigate anything, maybe organic or other materials?
Yeah, absolutely. So the reason rocks and metal work so well is because they're primarily either absorptive or reflective. So for an absorptive material, they ablate very easily because they absorb the light well. A reflective material generally ablates well, and also you get the added bonus of the material is reflecting plasma back onto your collection optics. Transmissive materials really present the issue. So in particular, looking at organic examples, there are plenty of studies using LIBS to analyze coffee beans. Typically, the reason you're doing that is to look for lead contamination or things like that. But we've been able to get LIBS signals on coffee beans, on cinnamon. Some studies will take leaves and dry them out, grind them up, and press them into a pill. And then you can perform LIBS on that pill a bit easier than you could on just a bare leaf. So yeah, while you do get a better signal off of highly reflective or absorptive objects, for some of these non-rocks, non-metals, you are still able to get a signal out of it.
So yeah, we had an additional question about whether there's any collimation optics going into the fiber. There's not in this case. We just used a bare fiber at the end to try to capture as much of the light. Any kind of optic we would put in front of there, we were concerned about it cutting off signal or clipping signal. So this fiber is in fact a solarization resistant fiber that's in our catalog, and it allows us to, it matches quite well with the spectrometer's range of 200 to about 1,000 nanometers. So we still can collect light. You can see even in those images Ethan had down to nearly 200 nanometers. So you have one more question. If using a Q-switch laser for non-thermal machining, specifically for hole drilling, how can depth of the hole be controlled while preventing the sides of the hole from being tapered?
That's a good question. I'd have to think about that for a second. Chris, do you have any thoughts while I'm thinking about that?
So there typically is a little bit of taper associated with drilling a depth of hole with one of these lasers. There's novel applications where people drill through transparent materials with femtosecond pulses, where they can get truly untapered holes with large aspect ratios. But for this, there is still the problem of material removal. So as you get deeper into the hole, it makes it more difficult for both light to get in and for debris to get out. So although there are some fluid-assisted processes to do that more efficiently, that is always a problem.
Yeah.
Okay, I believe that is all the time we have for today. If you haven't gotten to your question, we will do our best to reach out to you directly. I'd like to thank Ethan for his presentation. Join us again next week with Thorlabs lead scientist, Dr. Garwing Truong, as he introduces a patented novel crystalline semiconductor technology that has been shown to achieve cavity finesses of above 400,000 at 4.4 micrometers. You can register for this webinar by clicking the Register Now button below or on our website at www.thorlabs.com/webinars. Thank you very much for your attendance, and we hope to see you again.